Oh, that's right. We had a problem with Matt slides showing up on our video feed. It just wouldn't go. Gotta make sure things are working. I do have one. Okay, I actually don't have one.
Testing, testing, 1, 2, test, test.
Oh, he has it.
want to do the screen.
Yeah, well, I brought my own lunch, so this is perfect.
I'm waiting to have.
We're Bakersfield.
Or anything? Yeah, we'll get you some.
Oh, I forgot my jacket today.
Oh, yeah,
I'm
you guys
not
are
leaving
leaving.
anytime soon.
Need to build a little tunnel.
So, sorry.
That's okay.
I think I'm supposed to talk into your microphone, but what I can do is just borrow it, like I can hold it, and then we'll just give it back to you. You broke it?
I totally broke it.
Oh, I think it works. Whoa. I think the reason why we need the microphone is not for people here in the room, but for the video purposes, because I know Mark is one person who's hoping to be here, Mark Madera, so he wants to. Okay. Welcome, everyone, to this special seminar. We're thrilled to have visiting faculty, Duzgun Agdas here from Queensland University of Technology in Australia. So, for the record, down under it's summer right now, so you're supposed to bring a little bit of sunshine for at least your seminar, but clearly you're bringing the rain, which is actually good too. Both Australia and California share a need for fresh water. So really pleased to be able to have you here for the next two months or so, and maybe more if we can convince you to stay. You might have seen him around already, but he's already been infiltrating our various offices to find out what types of research we're doing, and is interested in doing additional collaborative research with us. So we're really thrilled to have him here with us. And so the idea for this seminar is to get a glimpse of some of the research that he's already been doing and his research interests, and then hopefully you'll get to meet with him either directly after this seminar or over the coming weeks. Note that he's a amateur basketball player currently, but he's had some some strong basketball experiences as well. So if you're interested in pickup basketball player as well, please welcome him to Davis on the basketball court as well. Anything else I should say?
No, that's enough.
Okay,
That's,
good.
that's enough. All right. Thanks, man.
Let's welcome Dustin.
Well, thank you. Thanks, Ben. Okay, so Yeah, I'm not sure about the basketball part, but the rest is fairly accurate. And we actually had the hottest day in Brisbane the day before I traveled here. Yeah, it's been interesting. I'm also told you had about 3 to 4 days of rain a year, so it's been, I think, 7 in a row now. So something's going on here. Anyway, so I didn't really have a title for the presentation. I just said the presentation, and someone said the title of a seminar, so I kind of made up one. But let's start with a brief introduction. So I put a picture. I didn't know why I put a picture, but I think it makes sense now if there is a video, okay, so people see what I look like. So I'm a senior lecturer of construction engineering and management, QUT. We are a relatively large research-intensive university. I think we have 50,000 odd students. We have a few of our master's, PhD degrees, undergrad, all of that. And I'm a senior lecturer because we still use the British system in Australia. So I think in America I'll be depending on maybe a junior associate professor or a very mature assistant professor, so somewhere in between. So I'm originally from Turkey. I came to America. Actually, I did all my postgraduate education at the University of Florida, which I worked for. I also worked there, I think, 3 years or so. Then I got a job offer in Australia, and so I moved to Australia. I also have they make us do additional training once we become academics, so it's fun. So I also have not sure why I have this here. I have a graduate certificate in academic practice, which was probably one of the most difficult things I have done my whole life, so I thought I'll put it up there. I'm a professional engineer. I'm a traditionally trained civil engineer, so I hold a professional engineering license in Michigan. It's you might say, why Michigan? Because Florida Board of Professional Engineers was, I hope this doesn't leak, wasn't very easy to work with. So I decided to go to Michigan to sit for an exam. I'm a lead AP for those, I think, is still around. And I also have environmental, I think, don't know what this stands for, but back in the day when the USGBC was involved in ASCE. So ASCE started with American, a few other agencies. They started what they call basically a sustainability rating system for infrastructure, and they also had a certification program or accreditation program for individuals. So I ended up taking that one as well. I'm not even sure if that's actually still valid or not. Anyway, so today I'm going to talk about 3 ongoing projects essentially that we've been working on. So the first one is basically one of the I think I'll talk about these. Let me just read the titles, then we'll get into details of them individually. So the first one is more of it's a direct collaboration with mechanical engineering people. So we are trying to figure out how to optimize, so to speak, HVAC systems for user comfort, which I'm pretty sure most of you have an idea is a peculiar topic. Our idea was, well, we can just use people as sensors for comfort, which is generally how these designs are, how these systems are designed. Second one is, this is with one of my PhD students. I coined this term recently because it's actually a closed loop supply chain, but circular economy seems a lot more, it's a lot simpler to grasp. So we are looking into construction products and how to reduce their impact, their overall impact from a life cycle point of view. And the last one is, we want to look into impact of this design and construction over energy consumption for social housing in Ecuador, specifically for this one because it's a project that's going on in Ecuador, but there's some implications for underprivileged communities, so to speak. Now, the interesting thing with this whole thing is this was not part of my PhD work. I had nothing to do with energy. So this is my first office in University of Florida. There's nothing too exciting here except for that this is the door. And just to give you an idea, this office is about, let's just say these are single units. It stretches about 2 more of these little squares. And my office was hot all the time. I couldn't figure out why because, it's an air-conditioned space. Why is it so hot? The reason it was hot was I sit on this side near the windows and I had my computers here. This is the exhaust for air conditioning. It was blowing air directly to, you don't see it here, not a great photographer I assume. There's a wall here on which the temperature sensor was mounted. So whenever the air conditioning will go on, it will blow cold air to the wall and then basically, the whole set temperature issue. Well, you'll be like, well, so I'm like, okay. So I call the facilities. They come and they reduce the set temperature to a couple of degrees. that also didn't work out too well. So what I would do is I would just go stand next to the sensor, or I also heard people use microwave some mayonnaise and put it on the sensor just to heat it up a little bit so you get more of an airflow. I said, this looks like a small example. Then, well, surely there must be a way. I mean, this cannot be the norm, right? Because I assume, because in Florida, you have a lot of heat, you also have a lot of humidity, and you cannot live without air conditioning. You'll have mold, you'll get sick, so there's a lot of health considerations. I said, well, this must be the exception, not the rule. That's when I realized, well, this was a retrofitted building, so not sure when the HVAC system was designed, how the space was used afterwards. So then I started digging this up. The more I dig it up, it became fairly more complicated. So my involvement essentially started with this, just being unhappy in my room because it was too hot. But the bigger problem is the disconnect between structural design, first architectural design, structural design, then you got the afterthought of HVAC systems and space utilization afterwards. I've seen people put drilled sheet metal to prevent the airflow. Some interesting stuff, but that's all on the operational side of things. So anyhow, so this piqued my interest, and I wrote a few papers about green building energy efficiency and how to do energy simulations. So I kind of self-taught on the technical side of things. Anyway, that brings us back to the current time. That was about 2009, 2010. So the first project I want to talk about, this is, we are at the deployment stage of this one. So human comfort is a complicated subject. So the main reason that we live in buildings is so it shelters us from outside. It's not too bad here in Florida, and some other subtropical climates is quite bad. Essentially, we live indoors. And some of you might be aware there is relatively old technology, relatively old knowledge about what the comfort level for individuals should be. So we use electrical and mechanical systems to keep people comfortable. And there's some comfort curves, I'm pretty sure you are aware of it. The problem is people are unpredictable, so we try to figure out what makes people comfortable or uncomfortable, and it seems it's near impossible to sort out how or what affects this decision making. But we said, okay, why don't we make some sensors, give it to people, so whenever they please, they tell us how they feel. And I'll show you some pictures of what that looks like. One of the ideas is we want to collect systematic feedback over a long period of time, pair that with sensor data about indoor air quality. We will also have some information from the building automation system about some of the other stuff that's going on in the ducts. And the idea is, okay, we want to have a granular picture because this is well studied. I think Ellen is not here. A lot of people, LBNL, proposed productivity savings or losses because of improper energy practices to be quite severe, and there's some order of magnitude discussions. But the reality is, the reason we don't do too much, I suppose, more granular energy management is cost seems to be a prohibitive factor. So we have a very customized design, so to speak, but we have all the information that's needed. That includes how much these sensors cost, what are the development costs of writing up the software for these sensors, how you need to interrogate with the building automation systems, and potentially how this will impact productivity. Because the main goal, my contribution is, can we actually do a granular cost study about having a almost an over-designed over-designed HVAC system for a commercial building that should have positive impacts on productivity. Okay. I talked about this one. Okay, this is what they look like. This was, I think, the prototype. That's what they will look like. So you got the cold, hot, that's the temperature, stuffy, dry, so that's the more or less the air quality. And the feedback, we are not too sure on this one because I think the best option is to not instigate the feedback, so we get organic feedback, but then they might not give us any feedback. And that's an issue with one of the projects we have on campus about the thermostat. Is that what's called? One of the issues you have on that one is you have very sporadic feedback because people provide feedback when they're unhappy. But we need more on this one because the idea is based on this feedback we will be able to change the characteristics of the room they're in. So hopefully they will improve their comfort. So this is the part that needs a lot of work in terms of having a granular relationship, because we know, comfortable people are more productive. But we don't know how that relates to long-term cost implications from a scalable hardware, software, sensor network type of thing. So it's not just, well, it's your energy bills, but can we justify installing systems of this sort? Because this takes additional work. This is not off-the-box solution that you use with a single set point that you have in a room, but we'll have to do a little bit more. So hopefully we'll come up with some numbers, and that will give us some indications of the cost, the scalability issues, and whether this is a good investment or not. Now, number two, so I'm going relatively fast because I'm hoping to have a discussion, and we're almost halfway through my allocated hour. And so if I'm going too fast, please slow me down. I can talk real quick, not on purpose. So the second one is Ben, you remember the talk about the cement and what was the cement and metals? Yeah, the EPIC Symposium. If someone finds a way to reduce the emissions associated with cement, there'll be a rich startup or something in that line, which is true. But the problem is we like cement because cement is good. Cement is a great thermal characteristics. It's good strength-wise. It's cheap to make. The problem is we use lots of it. So one thing that's not looked after is it causes a lot of issues with the construction in general. A lot of because the emphasis in energy mostly around CO2 productions and how much energy we actually use. When you use too much of a material, maybe the energy considerations are not as apparent, but we also have implications in habitat alteration and dust and a few other environmental concerns. We use too much cement because we use too much concrete. We use concrete because concrete is a great construction material. So there's alternatives to concrete, but they tend to be expensive. We also need lots of it, especially in developing countries. We do need lots of concrete, so it's material intensive. That's for construction. Construction industry produces, this is the producer of the construction industry, is the producer of the largest non-toxic waste, largest of which is also concrete. I think the number for so man-made CO2s, about 5 to 9% is related to cement manufacturing. So that excludes the operations and a few other things. So cement is bad. There's two issues. One, you need to use high heat kilns, which mostly use some sort of a fossil fuel. I suppose they are switching them to natural gas, which is better. That's not great. The other issue is, I'm not sure how much interest in construction materials here. The chemical reaction of making cement creates, it emits a lot of CO2s as well. So there's two separate processes. So what we are interested in is not necessarily making the cement, which is essentially that's the golden goose if we can sort out to find a way to make cement less CO2 intensive. But I feel there's lots of issues around that one just because of how large the scale is. This is the most widely used construction material in the planet. Not much work is done to what happens after we make concrete. So we use concrete, and then so you pay a lot of attention to CO2 emissions, how to make concrete, and what happens to concrete afterwards, that's not really well studied. Now, how do I know this? Well, we pretty much read everything under the sun written about waste management in construction, and it turns out the only emphasis is at this side. Basically, we try to divert construction waste from landfill, because landfilling is also expensive. I mean, the waste is non-toxic, but there is large amounts of it, and you might see examples of this. I'm not sure, I haven't seen a building being demolished. The reinforcing steel might be taken out, the concrete might be crushed for different uses. There's issues with recycled concrete use because you cannot use it for structural applications. There's issues that still persist. So when I give this talk to state governments, some sort of a state government, we have too many politicians in Australia. I don't know who I was talking to, but I was talking to some people from state government, and they had a moderator. He said, well, so there is value in dirt, so I didn't occur to me. Actually, he had a very profound observation. The problem with this is, when a lot of the construction materials are made obsolete, they are not obsolete from a structural point of view. They're obsolete because we don't want them anymore. So, and I'll give you an idea. I don't think we have a single case of reurbanization after, let's just say 20th century. Do you know of an example a single city was redone because all the buildings became obsolete and they need to be gotten rid of? And so, no. Okay. Right. So concrete is asphalt pavement, I think, has a design life of 30 years. But I've seen lots of buildings from 16th century using some sort of, I guess, a cement mix and some rocks. They are still around. I know you see those cathedrals in Europe. They seem to be doing okay, and they're designed in quite. I don't know what the technology was at that time. I'm not well versed in historical architecture, but modern buildings, especially modern commercial buildings made with modern concrete and all the metals in it, I don't think they become obsolete after 30 years or even 50 years. I'm talking about the structural components of this, which you use the concrete. Well, they become obsolete because you want to do something else. Like you want to have a nice, shiny new building, or you want to build taller. In our case in Brisbane, there's a new entertainment district. So they actually got rid of about 20 perfectly normal buildings. So I'm like, So one way to actually reduce the amount of concrete is we can use things longer. Well, we can't use things longer because we need the building functionality to serve a different purpose, because you can't have the same design as 1930s or 40s at this time. The simplest example is the HVAC systems or maybe some sanitation or whatever it might be. So we need to basically find a way to make things last longer. So what we thought of doing is, there's something called reverse logistics, essentially. We all know what logistics is and supply chain management is. Reverse logistics is you make upstream supply chain decisions to improve end of life cycle for the products. So, okay, can we apply this to construction? Because currently what's being done is diverting landfill. Recycling is not the most effective form of dealing with obsolete products, which in case of construction, they're not really obsolete. We make them obsolete because we tear them down or we crush them. So what does this mean? So right now we are trying to find a systematic way to assess alternatives for reuse, refurbish, repurpose. There's different reverse logistics strategies that is applied to manufacturing industry. So our goal is to, can we take some of these and show the impact of doing something other than landfilling and recycling and quantify this impact and perhaps come up with some life cycle considerations for the built environment. That makes sense? So that's the goal here, and this might be out of everybody's comfort zone, but I think it's quite important because there is lots of it, and I don't think it's going to change. Okay, so we need to come up with the numbers. The other thing with concrete that doesn't get as much attention is quite cheap. I think it's mostly because it's subsidized. I'm not too sure. I haven't got into the numbers game, but we will also get into that one. Because you don't use a natural gas you will pay at the retail in your household if you are using natural gas to make concrete. So a lot of the overall impact doesn't get fully understood because we don't really know the details of the intersection between energy cost and CO2s, because I think at an individual level, the emphasis is we know carbon is bad because everybody's aware of climate change or global warming, whatever you want to call it, and we want to reduce it. We also know we pay for bills, so that's what we know. That's what most of the consumers know. The issue, I think, is that the actual picture is a lot more complicated, and this industry is a particular example of it. In America, I think I asked this question to you as well, Ben, how much the Caltrans spends on construction. I know, it's a quiz. I'll take some answers after we are done. I know we don't. It's okay. The last one, not the least, is this actually a really exciting project that I didn't start. I was just brought in after they had some preliminaries done. And so I have one of my former PhD students. He's working as a professor in Ecuador now, and They said, we have a project, would you like to get involved? I said, sure, what's the idea here? Their idea was to look into embodied versus operational energy considerations. And embodied energy is something quite similar to this concern, because we tend to focus on operational energy. We don't really look into embodied energy is a common term to everyone in the room, I suppose. Okay, so I said, let's look into embodied energy for social housing. So Ecuador, these are not my words, as far as I know, has gaps in income, which means there's a lot of government services needed for making up for housing deficits. So they have a lot of people who probably migrate to larger cities. I think Guayaquil and Quito are the two major cities. And there's a shortage, so the government basically, they have programs to build housing for people. Okay, I think we refer them as social housing. So these are to afford people or underprivileged people to have some sort of accommodation. So that's the idea. And what we want to look into is the original thought was, let's look into embodied versus operational energy for typical construction methods used in social housing projects. So, we did all the life cycle analysis and energy simulations and all of that. And there is not that many options. So we thought, when you say construction, one of the classical arguments in construction is, well, design is unique, everyone does it. Well, it turns out that's not really the case when you are doing social housing. There is 3 different wall materials they used, or construction methods, and 2 roofs. I think this is concrete masonry, load-bearing walls. This is insulated concrete forms, if I'm not mistaken, and you have either a slab, it's a concrete slab, or zinc as the roof material. I cited the paper. You can see the pictures of what these things look like. So we run the numbers. Okay. So this is the insulated concrete forms. I'm hoping I'm saying that correctly. With a slab. This is the annual energy demand for a typical social house in Guayaquil and Quito. Guayaquil is a coastal city, so it is really hot and humid. I think Quito, I have not been there. It's in the mountains, so it's a little bit drier, so that's why you see a difference in energy demand. But what's peculiar here is these are available construction methods for government to make decisions on how they're going to build social housing. And this is the energy demand. I think the numbers were up to 69%. Again, I might be incorrect. But here is where it gets important. I guess it gets interesting. And this, you can see these are the differences. You can see different pieces of lighting, heating, etc. We made some assumptions when we come up with these numbers, especially in the operational demand side of things. So when we use Energy Plus, we assume the rooms are kept at a certain temperature, which may or may not be true. This is the demand. I'm not sure if people actually use this much energy or not. As you can imagine, people who need social housing also have issues paying their bills. And what I still don't understand why, when you have this option, you'll actually invest in other building types. These are not different designs. These are the same design with different materials, because they are very simple structures. Well, then another thing is, this is also a total energy for different, this is what we gathered from the literature, and this is what the social developments, these are very simple structures. These are structures people basically who are trying to make the ends meet need to live in. And we can have substantial differences in what the demand for energy at the operational phases are. So I still don't understand why they don't make everything with the insulated forms, because over the life cycle of this building, we also, there's some technical details. If anybody's interested, I can send a paper to read. Operational energy is much greater than the embodied energy, because these are simple structures. But what's more important is, most of these people can't afford to have proper, they don't have enough means to have the energy to keep their houses conditioned to an acceptable level. What does that mean? The time I spent in Ecuador, I think at this stage I went 2 separate trips. I spent about 2.5 weeks. I was not in my bedroom without there's no central air conditioning, but there's a window unit. I sit in front of it and crank it to maximum. at all times because I could not stay indoors. It was that hot. I was so uncomfortable. That's the only way that I would be able to stay indoors. So what we don't understand is, given the scenario, given the inaccessibility of the energy, why you have different construction methods, because the energy demand is so vastly different for different methods. We don't know. So that's one of the things we need to sort out, because these are policies made at the central level. This might be an issue with cost. Maybe one of the methods is more expensive. If it's more expensive, we can easily justify looking at the utility payments over the last 20, 30 years, because I think government also have programs for subsidizing energy for people so they can afford it. It might be skill, construction skill. Maybe there's an issue with that one. Material availability, maybe the insulation material is not really available in the country. We don't know. So those are the things we need to look after. There's also this term coined in the UK as termed fuel poverty. That's when people can't afford fuel. I mean, it's a general term, I suppose. They can't afford energy bills to keep their houses warm. So I think it's good, because different people get impacted by this separately. But I think it's a bigger problem, maybe not bigger problem, but it's from a numbers point of view, I think if it's not now, it's going to be a bigger problem, just because there is so many more people live in warmer climates. And I think there's implications on public health, food security, whatever you want to call it. So that's our goal here. We are trying to figure out what can we do to basically move from different options to this particular method that's available. This is not something we propose. So this is a method of construction that's available to the country. Basically try to enforce why they should use it. The other issue is most of these are detached homes. When you have multiple detached homes, which means you also need to provide a lot of infrastructure to those detached homes, pave a lot more roads, which creates issues. And now we are trying to model the heat islands. There's few methods to do this. Satellite imagery is one. Things recently, MIT published a little tool that you can model urban heat islands a lot more granularly. So there's an attempt to fix that one as well. And I put the term energy justice because I don't know what that means yet. My wife is an environmental scientist, so she's a lot smarter than I am, and she told me a lot of issues on environmental justice, that the impact of development that has on different socio-demographic subgroups. I think this is going to be very interesting pretty soon, because we look into energy security from a global perspective, and whatever it might be, but I think different parts of population, different parts of the world are subject to this at a much significant levels, either for better or worse. And this might be an interesting opportunity for us to coin a few things and maybe look into how development in Ecuador, or we are also doing something similar in Australia, basically looking into last 10, 20 years, looking into satellite imagery. If we are lucky, we might be able to get some satellite imagery that will give us a fairly good idea about how hot the city centers have been, how this has changed over the last 10, 20 years, because we also can estimate how much the development change or contribute to this impact, hopefully, and try to not really draw conclusions, because I don't feel very comfortable, but at least do some preliminaries so we actually start treating, I think, energy with a little bit more detail, rather than just talk about reducing your utility bills or increasing the use of renewables, which are very important, but I think the actual picture is a little bit more, there's a lot more intricacies, and we want to figure those out. So that's it. Go ahead.
Sorry, I'm a little confused on that
This one?
graphic. Different, no,
Yeah.
this.
Yeah.
So, construction methods,
Yeah.
and
No, this is the operational.
pardon?
Operational energy.
Okay,
Yeah.
operation of those buildings, so lighting,
Yeah.
HVAC. So clearly,
Oh, no. That's what I'm going there after this. I don't know.
What's the difference between the two different ICF?
This is it's a metal roof. So the first one is this is the wall, the other one is the roof. So you got 3 wall types, 2 roof types.
So it's the roof that's
Yeah,
driving.
yeah,
Okay.
yeah. Yeah, I don't know. So it might be cost. I don't think it's cost though, because it's done. But these are not things that we suggested they do. These are the different modes of construction that's used. It might be something new. I don't know. So that's why we need to go talk to people about it.
It's like it's
Go ahead. No, not as much. Keto can be a little bit, again, these are all, we have annual, I don't want to bug the presentation with all the details, but we have the annual demand for both cities and in the paper. So Quito is, I assume it gets colder in winter, I can't tell on top of my head. So Ecuador is, the country is a subtropical country, but Quito is in the mountains, so I assume it gets colder at some point. Yeah, there might be some demand for heating. Yep.
How is that related to, for example,
Well, the best, yeah, that's a good question. So that's what we are trying to suss out at this stage. So the best option is you basically use the building as long as you can. If you can't, the next option is, well, can you refurbish the building and keep using it? Well, if you can't do that, can we actually take elements of the building? And this is where maybe manufacturing or modular construction can be a bit more important. The problem those things didn't get as much traction is it's an economies of scale thing. We don't use them, not because technology is not there, it's just not, there's not a good business case for them. So what we are trying to figure out here is that to answer the question you asked, so what's the difference between refurbishing a building or basically taking it apart? If you had the option to take it apart and use different building components to make something new, either a new building or use them in a different application. Go ahead, David, sorry.
are you thinking more about
Yeah. No, we have them. We can do it. You can right now. I mean, I was I don't know about California, but so it's one of those things. So according to the housing authorities in Hong Kong and Singapore, they can do 100% off-site manufactured buildings.
Yeah.
I'm yet to see them, but they keep telling me they are building them. I'm pretty sure they are. The issue with this is we don't have the critical mass to make these things financially viable and figure out some of the issues and stuff. Yeah, basically the downstream supply chain, you need to have enough suppliers, you need to have materials need to be manufactured in a certain way, you need to have standardization. The typical manufacturing problems will apply to construction as well. The reason it's not used is because the regular construction works, unless it stops working. So I think the cost is the key here. What's the actual cost of concrete? Not because right now it's what you pay for it. But I don't know if that's because you have that one and the rest of the plan is like, hey, 10% CO2, cement is terrible, but we still keep using it. So we are trying to figure out, but it's the design. You got to start at the design phase.
And if we're not
I think so. Well, look, the latest I've seen somebody was suggesting is cement tax, which I don't think is going to work out because this is I can talk about Australia. So construction is the number 2 source of employment in Queensland, and I think it's number 1 or number 2 contributor to GDP. So it's a huge market, and it's very hard. There's a lot of inertia. So the issue is how do we because the technology is available. I mean, you can do it. I mean, concrete is not that hard to work with, and it's actually there's a lot of times they use prefabrication, but it's in parts, and it's not for the sake of extending the useful life. It's just easier. That makes sense. So it's more or less, can we do a holistic assessment of this thing and give different options? Because if we can break this thing down with respect to cost, emissions, resources needed, whatever it might be, then it will make a better case for why maybe there's a need for a policy change. Because the government is also a big source of ownership, I suppose, from, they own their own buildings, just like universities are. I mean, UC Davis is probably the largest owner of construction portfolio in, I don't know which county you guys live in, but you know what I mean? So if there's a university makes a policy about certain, but there needs to be a justification to why we need to do things differently. It's not just, so that's what we are trying to do, basically give people more tools to make a better decision.
We actually had a presentation here that talked a bit about cement production.
Yep.
How the carbon release in the clinker production can actually be reabsorbed from the atmosphere as concrete structures are like decomposing,
Yeah.
essentially, when they're torn down. Is that sort of a component of the life cycle analysis? Is that something that would sort of fit in?
I have never heard of it. If it works, it's great. So because I'm not a material scientist, I'm a construction engineer, so I don't know. The short answer is, if something like that works, which is great, but I mean, I think my main concern would be we need to look into dynamics of who uses most of the concrete. I mean, we use some of it here, but there's interesting graphs with the level of development and construction spending. In most developed countries, you'll spend all of your money on maintenance and rehabilitation, and developing countries will go up. So is this a policy for those guys? Because it will come at a cost, at this stage at least. So can we actually bank on solutions of this sort? And they might, I'm fully supportive, but at this stage, I think if we can use existing technology, and we can do prefabrication, we can do modular construction, we can do it to make an immediate impact while people are finding solutions at the material side of things, that would be great. My concern is concrete has been around for about, I think, over 1,000 years. I'm recorded on the record, so I would have said 10,000 years. I don't want to say 10,000 years. This has been used for a very long time, one form or the other. And you can see, and the reason people use it, it works. It still works. It's great. It's just not, we just can't deal with the volumes of it. So the problems, what we are trying to do is look, what can we do now? Right? So while I think the technology is going to come at some point, we are going to figure out a way to either do carbon sequestration or something in those lines. But I'm not well versed to comment on it. Good.
I have some questions about the first project.
Yeah.
Deployed, how did you decide
Well, that's yeah. Sorry. Okay, go ahead.
and then kind of, I see kind of, it looks like a
It's totally homemade.
how many did you actually make and deploy, and
Yeah.
temperature, humidity,
Yeah. Okay, so one, they're not deployed yet, so we are going to deploy them. It's in a, I think it's got technology center, it's something like this, at the University of Florida, not on the campus, but it's basically it's an office building that's rented out to startups, etc. So we'll give it to as many people as that are interested, so facilities are supported, but it will depend on how many people want to take it on. That's number one. Number two is it's not just a screen, so there's a bunch of sensors in it. So it will actually collect. That's one of the reasons you want to couple the actual sensor data with the feedback. Number three, stuffy and dry is just to keep things simple. Because if you think about the comfort curve, you have the temperature and you have the humidity at some point, if I'm not mistaken. So it's a basic indication. You asked one more question, right, Ben? The other one was?
What sensors are
Oh, that's a good question. I know we have the temperature, CO2, and a few other things, but I'll get back to you. I don't know the exact number yet. I mean, the exact specifications of them. Ben, you asked one more question. That was the...
No, that was what sensors.
Okay. So the idea behind this one is there was a pilot at the University of Florida campus as well that I want to talk to Ellen's group about it. So they actually did this turn things on and off with the occupancy counting, etc. Look, what's interesting here is I don't think it's this is not super unique. I think there's been many attempts to do stuff like this, but we have control over the whole process, and that's why the sensors are not purchased; they're made. And the option to interrogate the automation system that gives us some interesting feedback, hopefully. But there's still stuff going on. This is not done yet. So the sensors are finished. I think they're about to be deployed.
And then how are you capturing
Ah. Well, the carrot is the better quality. So it's better comfort. So they changed this thing. The carrot stick. So hopefully we will be able to actually manipulate the HVAC systems to actually improve how they actually feel. Because if you think about this, the ultimate goal is to individualize comfort for people, right? The difficulty with that one is you don't really have the either mechanical granularity. I mean, not too many people live in individual offices with VAV boxes and all kinds of sensors to do things, but this is as close as we can get. So the idea is they provide feedback. I think the money is still on the table, but it depends how much money is left over the project budget, because I'm definitely not getting paid from that one. So things are tight. Those are the experimental considerations we got to suss out. The problem with asking for feedback is you kind of force the feedback. It's not really organic feedback. But then the problem with organic feedback is you will most of the times won't get it unless they're uncomfortable. But I mean, I think that might also be that might be enough to actually constitute what's in between. Because these are extremes. I think you will get the feedback either they're mostly hot or cold. So they'll need to be sorted out.
some work that LBNO's done,
Yeah.
other groups have done about productivity associated with light levels or temperature.
Yeah.
Yet there's also a kind of different cultural kind of norms that
Yeah.
and so the assumption is that there is some either number or some attribution that if even an individual has a certain level of optimal productivity, like some thermal
Yep.
comfort level. And so are you aware of kind of studies that actually validate that? Like there's self-reported productivity versus actual
Yep.
productivity versus, my preference for thermal comfort, but am I more productive when I'm actually cold?
Yeah.
You know? Or
Yeah.
am I more productive when I'm hot? I'm like sweating. Or I don't know what
Yeah.
the,
And that's a valid question. Yes, there has been some on call centers. There's been some on repetitive tasks. Unfortunately, that's a great question. So my response is, you are absolutely correct. There's no perfect correlation between improved comfort versus improved productivity. I can tell you, lack of comfort is probably, I guess it's what's the term I'm looking for? Better comfort, better productivity, maybe. No comfort, better productivity, I don't think so. So we have the weaker of the two correlations we are dealing with here. And our goal is not to do that one because there's enough evidence on literature, and I think the LBNL, one of them was in order of magnitude, I think hundreds of times in productivity costs because of energy malpractice, etc. That's not really my goal here because I'm not too interested in what they do with their productivity. But one reason the energy, again, this is where I think that what energy is perceived as is what's critical here. What we assume is, well, I can tell you from first-hand experience, every single facilities manager will tell you it's too expensive to put VAV boxes in every single room. It'll be too expensive, we cannot put sensors everywhere, and maybe it's true. But when I tell them how much it costs, well, we don't really know that one, right? There's always this argument, okay, it's going to cost us more money, because that's the major driver here. We want to reduce our energy bills. I mean, there's additional benefits to CO2 reductions, etc., but the immediate benefit here is energy reduction or utility reduction, whatever you want to call it. What we can do here, I'm hoping, is basically give more of a complete picture what it costs for us to design a system of this sort. When you are absolutely right, it might not change the productivity, but then you have the right, or you have the option to make a better decision about how you do your energy policies. Because I'll give you another number. Do you know how much you guys spend on utilities in a given year on this campus? Yeah, $20 million, right? That's what I heard. Do you know what's the budget for UC Davis's? Yeah, it's $4.9 billion. So, and this is where the whole argument comes in, and you have a great point. Look, $4.9 billion, most of that is salaries. 20 million, I don't know, something in billions, maybe. So that's always been the argument. Maybe if because 1 or 2% productivity improvement is not too hard, and I believe there is some compelling evidence around this. They have done this in, if I'm not mistaken, I'll dig up that paper for you. They did it in a call center or something with repeated tasks, so you can actually see what's going on. I think my argument is you are absolutely correct, but I don't know what decisions are made or how they are made, because they are made on the basis of, well, it's too expensive, so we got to find that's the argument, right? So you got to find a balance between over-sensing, under-sensing, sensing just enough. Like I heard that from our facilities people, the sensors were too expensive, temperature sensors, they're $5. I mean, it's not too expensive. Now it might be difficult to integrate with your building automation system because you are buying an off-the-shelf product that works with, single VAV box with a single sensor. I'm not even too interested in the VAV boxes or the sensors, but if someone tells me it's too expensive, well, maybe it's not, I don't know. So that's what we are trying to figure out. If it increased productivity, which we will attempt to do it, but that's not our number one goal here. The goal here is how can we design a system that will improve comfort of individuals, for better or worse. I don't think it's going to negatively impact their productivity. So that's not my concern. Our concern is, look, let's put some figures, let's give people not people, in this case it's me, give me some ammunition to make this case for better energy management. I think that's what it is. Yeah, I talked to Ellen about that one. Yeah, that might be also interesting. The issue with that one would be that it's very difficult to sort out. I think it's a very interesting problem, but we also need to think about scalability of these things. So there's a novel project. I think it's a great project here. This is, again, my interest involvement is I'm not going to do I'm not a mechanical engineer, nor I want to be a mechanical engineer. It's to see, can we actually scale systems of this sort? This is a homemade solution that's going to be implemented in a commercial setting. But it will tell us, look, can we actually do this thing at a greater scale? Because most of these studies, man, productivities, the controls, automation controls, etc., they're all done in 1 or 2 zones, maybe a building if you're lucky. There's about 1,300 buildings on this campus. University of Florida, about 1,000. So we can have these novel solutions in different places, but when you want to do scalable, large-scale solutions, you also need to have the numbers the cost numbers essentially to back up what can be achieved. Great. Okay.
So just so you know, I would like one of those sensors. But just so you know, Duzgun's office, or not office, but he's got a cubicle right now. Visiting cubicle, just in the other building over here, so you're going to visit him. He'll be there from time to time, and I'm sure he'll reach out to you, which he hasn't already, to find out those Yeah, it might be worth sitting down and hearing. So, you actually are installing it. You said was it installed? They don't have working yet still? There's a private sector company called they're based out of the UK. And they, well, Teresa already developed sensors that
There are various air quality monitors, but what Arby Well
I did say.
I'm not doing.
Oh no, the white paper stuff is.
we're just starting. We're the same. The sensors are installed.
You know, like what does that look like? In October, it's always negative.
They only take a measurement right there. Take a measurement.
Like it's really something like.
Actual measurements. Yeah, measurement and feedback. Yeah. You can't really rely on the perception. As far as air quality.
So it's like two parts. Part of it. I was looking at the stuff this morning and I was like, okay. Took it off and it's like, okay, why you keep your lunch? Like, what's the, because I think the estimates are like 80% of the load can be served in like 4 years. Like, it feels like that. So it's like, why do you keep forcing them to buy these, like, contracts if they're not going to be doing this? Like, you had SCG come in, and they basically said, yeah, we're out of the commodity business in a few years. So, like, they put kind of already into that contract, so they're not going to be starting loading anymore. No, so I don't know. Yeah. Yeah. But, yeah, exactly. And they themselves are having trouble right now with that just because lack of credit and lack of funds. I know Valleyton Energy basically contracted out all their procurement to SMUD, so SMUD's doing all that for them. So it's just like, I don't know. Yeah. Jimmy. Yeah. I have sort of a position lined up at Lawrence Berkeley. Lawrence Berkeley National Laboratory. So, yeah, it's, yeah, DOE. Yeah, DOE. And basically, I can work there if I want to, but at the same time, I just like this stuff like this, like LPA stuff, and just like I am trying to get into like more policy-driven stuff. Like we're just like consulting company or something. Like, that'd be kind of fun. But I also have to acknowledge that my background is engineering, and unless marketing was an engineer, I can go through those. Well, I'm interested in this stuff, and I read, music media and dive in all the time, and but I don't have like the coursework for it, or like, I can't say like, oh yeah, I've taken like all these courses I've taken. So my sir, I have a spot where I'm happy with like doing stuff that I'm not necessarily like comfortable with, and also just getting paid well and being happy.
They can censor